IB, Department of Clinical Neuroscience, University of Oxford. Then she worked in as a postdoctoral fellowship in different universities, uh, Massachusetts Institute of Technology, General Medicine. Then she has also worked with Harvard Medical School before joining IAAC. So her area of interest include machine learning, deep learning, medical image analysis, neuroimaging, domain adaptation. She is involved in the development of computer-aided analysis tool for uh, in general for healthcare. She has also published some open source tool which is available in open source repository like GitHub repository and all, WinGit lab. Thank you, madam. This will welcome you to this FDP. Over to you, madam.
Great. Thank you so much for the kind introduction. Sir, how long should I keep the talk?
Madam, it's your choice, madam. Duration given is 1.5 hours, sir. 90 minutes.
Is there a break in between or can I just go ahead with that?
It's your choice, madam. No issues.
Okay, great. Hi everyone. Thanks, Professor, for the kind introduction. So let me quickly share my screen. Just give me a second.
Yes, madam. You can share your screen.
Yeah. Okay. Are you able to see my screen?
Yes, madam.
Okay. Okay, yeah, thanks again for the kind introduction. So today I thought I will talk about the specific topic on new deep learning in neuroimaging for precision medicine and low data regimes. So I was asked to talk more about brain tumors and neurological diseases. So I thought I will also on top of that cover other wide range of topics as well. So, I think before going into the topic, it would be good to have a general understanding of medical imaging modalities and what they cater to. So, let's look closely at the imaging modalities. There are specifically two needs for which the modalities are used. The first one is clinical needs, and the second is scientific needs. So, what do we actually mean by clinical needs, right? So, these are macroscopic clinical imaging modalities like what we normally go through in clinical practice: ultrasound, MRI, CT scanning. So all these things was or what we call as macroscopic modalities. I have shown a few examples here. So their main aim is to have a clinical diagnosis and also progression tracking and other clinical applications. So they are faster and also cheaper to acquire compared to microscopic modalities, which is basically what caters to scientific needs. And there is also, like, various range of radiation exposure that might be associated with these modalities, but mainly used for diagnostics and clinical workflow. The second type is what we call as scientific needs, which helps partially in diagnosis. For example, people go through the histopathological scans, biopsy, and all those things. But then they are mainly used for scientific understanding. So how the disease progresses, what kind of cells are present in particular type of tumor. So to study at microscopical level, for instance, even my work at Harvard mainly involved the study of macaque brains, of the histopathological data of brains, to understand how the connectivity of brain happens at microscopical level. So this is what we use for scientific needs for better understanding. So they might be used for clinical needs in distant future. Then coming to applications of medical image analysis, which we work majorly in this domain, the very first one is diagnosis. So given a specific modality of the imaging, so what can we understand about the particular disease? So for instance, let's say that there is this brain MR given, so we get these lesions, right? So we diagnose that there is lesion present. These lesions might be related to specific um, specific disease type. So what can we understand about these particular lesions, and how can we diagnose the lesions and the disease as at the earliest possible? A second is monitoring. So let's say that there is a disease that we are monitoring, for example, tumor. So what can we understand about the time progression of the disease? at two different time points or multiple time points, how these tumor lesions vary, right? So the volume changes, the shape varies, and how these things are catered to in this particular modality. Like how can we use this modality to change the, to understand the changes in the disease lesions. A third is treatment. So the very good example would be, let's say there is a tumor patient, the doctor wants to do a surgery. Now the doctor wants to know whether doing surgery would be helpful for the patient or not, because in most of the cases, above 90% of the cases, the tumor actually relapses. Like the tumor comes back again, becomes a progression stage again, especially in brain tumor. Gliomas are heavily progressive in nature, they aggressively progress. So oftentimes what happens is that the doctor performs the surgery, they remove the core, but even then the tumor comes back after a specific period of time. So this gives the patient some more time to live, basically. So now AI can use in can be helpful in understanding whether the pre-treatment and post-treatment, what type of changes will happen, what will be the variation in the volume, and what is the chances of the survival, number one, and also what's the chances of these tumors coming back. Research study, as I told you, most of the microscopic modalities are mainly used for research to understand more about the anatomy, physiology of the population, or mainly to understand how the what kind of cells are present in a specific pathology and things like that. So mostly at cellular function and structure. A typical radiology workflow looks like this. The first is acquisition of various images. So this is a skilled radiographer performs the image acquisition. So they might actually have, they might have certain years of expertise, and the more the years of expertise, they'll be able to set very precise imaging protocols so that we can get a high quality image. The second step is what we call as pre-processing. So even if we have a very good quality image, we are supposed to pre-process. So this can actually include very specific steps that is involved in the particular modality, which is very relevant to our research. To prepare the image, which is conducive for the research, we have to do this kind of pre-processing to make the images of a good quality. Sometimes we might have to reduce noise, sometimes we have to enhance the contrast, sometimes we have to remove the specific parts of the image that is not relevant to our task. So all these things are included in pre-processing. The third stage is, we have the image. The third stage is these imaging based tasks. So this is where most of my work falls in, and this is where I'm going to talk about today. And once we have these metrics or quantitative measures available, they can be reported to the patient. That's the next step. And finally, we have these measures integrated into diagnostics. We do clinical trials, and finally, the tool is integrated into clinical workflow. So, as the professor mentioned when he introduced me, so I have over 10 years of experience in developing these tools for clinical practice, and three of my tools are already integrated in a few softwares developed by University of Oxford, which is widely used by over 1,000 to 1,500 labs across the world. Right. So this is where we do trials, and then finally, so these are open source tools. So mine does not undergo clinical trials, but if a party has commercial interest in their mind, they have to get FDA approval. For that, it has to undergo very stringent clinical trials. So that's the last stage. But today we will be talking mostly about the image-based tasks. So mainly I was talking about detection, where you say whether the particular scan is healthy or pathological. And the second stage is characterization, where we segment specific, pathological signs. For instance, segmentation of tumors, which are basically detection of the tumor boundaries. That is what we call as segmentation, semantic segmentation, where we identify tumor voxels versus background. And then diagnosis, based on what we have, we diagnose what stage the disease in, and so on. Staging, right? Again, the severity of the disease. And monitoring, where we see across different time points how the disease is progressing. So for instance, here it is actually going smaller and then it is increasing, right? So as per the time point, how the risk or the quantity of the lesion in the particular organ is changing. So, in this particular talk, I'm going to focus on the three main applications. I will also introduce the other applications as just as an introduction, but these I will talk very deeply about. So, the first one is anomaly segmentation and early diagnosis. So, these three tasks are extremely important in precision medicine. So we have a lab of AI in precision medicine in our department, where we work very closely with clinicians to ensure that we have differential diagnosis and precision medicine for subjects. We work on different projects related to that. So one of the items I'm going to talk about is fully supervised and weakly supervised segmentation. So so you might already know about these fully supervised and weakly supervised methods, where we have a proper ground truth annotations by experts. That's when we can perform fully supervised methods. And weakly supervised is where we do not have proper annotations, but we have weak annotations or weak supervision, where from which we develop models for specific tasks. And they mainly cater to extraction of biomarkers for early detection of neurodegeneration. And the second aspect I'll be talking about is hardware aware lightweight solution. For instance, knowledge distillation. See, we all know that deep learning methods are extremely time consuming in nature, and also they are very complex. Like, computational complexity of these models are extremely high when compared to conventional machine learning. So we have this, and we don't have such computationally complex setup in all the clinicals setup in India, right? So clinics do not have this. So we want to develop lightweight solutions that can be easily implemented on edge devices. For example, it can be easily implemented on your mobile phones. The processors in the phones are not as powerful as your systems, machines, the clusters we use, the servers we use. So how can we use very lightweight models that can actually be implemented very easily on the mobile phones, or some rudimentary system in a clinical setup, right? Because the clinicians need to understand that as well. So I will give you an example for that we work on in our lab. And the third one is explainability and low data regimes. So these two topics are extremely important in medical imaging. In fact, these are the primary topics in medical imaging for two reasons. So explainability is where we provide a bit more information to the clinician about our results more than we usually provide. I'll give you a simple example, right? So let's say that we are looking at a subject and the model says whether the subject is healthy or not. Now, the next question from the clinician is, so how do you say that, and why does your model say this? What are the features from the image that the model considers before it makes this decision of healthy or pathological? Right? What are the regions, for example, in the brain that the model considers before saying that the subject has degeneration or dementia? Right? So explainability is very important, because the two major stakeholders in in medical imaging, at least, are clinicians and general public, and both of these category of people do not have the technical expertise that we have to develop these models. So they have the right to know what is happening in the data, or what is happening, why is the model making those decisions. And the second thing is low data regimes. So we go and ask the clinicians for data, and oftentimes it's not possible to share data because medical data is highly sensitive. There is not a lot of data to start with, because digitization is a very new and recent procedure. People do not do that often, and most of the records are non-digitized, right? So the data we have is very small most of the times. So we suffer from low data regimes. And also the other issue is the annotations. So the doctors are ready to share data to some extent, but for them it's a huge burden. Already there is a burden on them because of the population in our nation. So it's not possible for them to sit and annotate for hours. It takes 2 to 3 hours for certain disease signs, especially when they are small. They have to search for it and look closely in a 3D volume. It easily takes 3 hours per volume, right? It takes a lot of time. So annotation and even the data is very scarce. So that's why we need to work on low data regime. So how can we consume very less amount of resources and still provide a very robust model? Right. So we move into our first project, which is anomaly segmentation and early diagnosis. So before going into this, I just want to say that please stop me at any point of time. If you have any questions, if you raise your hand, I won't be able to see. So please make some noise, and I can, wait for your question. Right? Okay. Here we are going to talk about white matter lesion segmentation. Yes. Hello.
Madam, it's a false alarm. I see.
Okay, okay. Right. So the first topic is white matter lesion segmentation. So here we have a specific kind of lesion where, so the dark structures you see here are ventricles. So these are normal anatomy, but in this case it is even dilated a bit, but that's okay. So they are supposed to be there. But these bright regions here, so these are not supposed to be there. So these are what we call as the early signs for neurodegeneration. So this is what we call as hyperintensity, which can be as early a sign for dementia, neurodegeneration. They are even associated with bipolar disorder, schizophrenia, and they are also associated with cerebrovascular disease like stroke, right? So these lesions which are closer to ventricles, they can even happen with normal elderly population. But then you see these small regions here, the small lesions, which are virtually, non-detectable. So these are basically from vascular origin, found mainly in hypertensive subjects. They are the main sources of main factors that are associated with stroke. So identifying them in the early stage will help us in identifying the proper treatment plan for the patients, and also it will be useful in proper drug administration and stopping the disease from progressing. So that is our first aim. So here we developed, I will talk about the architecture, model architecture in the next slide. So here what I want to focus on is that we did a combination of two different loss functions. The first one is dice loss function and the second one is cross entropy. So for those who are not very familiar with how deep learning works, so we have a model, we have different layers, and in the forward pass they are used to predict the output, and in the back propagation, which is basically the reverse process to forward pass, and it happens in the opposite direction. So the gradients are computed, and there will be something called as loss function or cost function, where you have the output and there is a manual output. So you compare both and you have to minimize the discrepancy between both. This discrepancy is usually specified as sum of the cost function. So your aim is to minimize this discrepancy or minimize this cost function or loss function. So these are the terms for that. So the model trains, iteratively until the cost is minimum and the model has robust segmentation capability. So here we are using combination of these two as our cost function. So how does it work, right? So our main innovation comes from the fact that we are changing the cost function accordingly, mainly the second term. So here the dice loss is more specific to the structures, whereas the cross entropy is at image level. So we take the whole image and we apply the cross entropy loss for getting the, for minimizing the discrepancy between the predicted mask and the annotated mask. So how do we do that? So I was telling you that these regions, the small lesions which are away from the ventricles. So if you put a model, what will get detected very easily are these large ones. So you see these large ones, they will get detected very easily. These small ones are going to be tough. And we know that these small ones are important. So what we do is we want to increase the weight for those spatial weights for these regions. So that's what we are doing. So as a first step, we take the distance from the ventricles so that the region away from these ventricles get higher values compared to the ones closer to ventricles. However, we cannot keep going until the end because then we would hit the gray matter. And the gray matter is a normal anatomy. We cannot increase the weight for that. Then we will have a lot of false positives along this gray matter. So I also take the weights from the gray matter. Now we want the weights from the ventricles and also from the distance from the ventricle and also distance from gray matter. So if we combine this, we get a map which has high values in the middle and slightly lower values as it gets closer to the ventricles. And this is the map we use to weigh the loss function. Now the loss function has higher weights or higher importance to the regions that are away from the ventricles, and this improved our segmentation accuracy, especially in this belt which is farther away from ventricles, and we were able to successfully detect all these small lesions, right? So if you see here, the brown curve, the brown box plots are our proposed method, the TrueNet, and the violet ones, the purple ones, are state of the art method. So we can see that our method performs on par or better than state of the art in 3 data sets that we tried, and the average improvement was about 20% for our method, and for the dice value it was on average 15% improvement in dice. So now coming to architecture. So what was the model architecture that we were using? So we were mainly using the unit backbone. So here I have shown the unit model for those who are not very familiar with the unit model. So the unit belongs to an encoder decoder architecture. So the encoder extracts the texture based features, and then it consecutively downsamples the image, pulls the image, and then in the decoder part we have upsampling, where we lose all the very localized texture based information, but what we have here is the location of the object. So encoder has texture based features and decoder has location based features. Now these skip connections we have, the arrows that go directly from encoder to decoder, are extremely important because these are the arrows that are going to combine the texture based features with these location based features to get the final output. This makes the unit model a very powerful model for medical image segmentation. So now coming to our actual architecture, so we use this 2D unit across the 3 dimensions of the image. So we have 3D volume, MRI volumes, and then we apply these units on all 3 directions or dimensions, however you want to call it. So this is what we call as axial slice. This is, as our along our brain direction, and then this is along our sides and this is from our back, so anterior posterior, and this is basically mediolateral, and this is basically dorsoventral direction. So now we apply in all 3 directions, and then finally we obtain the final output by averaging the prediction across 3 directions. Now we didn't stop there. We wanted to check if we can actually apply the same model for tumor segmentation as well. So this is slightly challenging, more challenging than hyperintensity, because this is not a binary segmentation, this is multi-class. As you can see here, there are multiple labels here. So we have edema, which is shown in red color, and we have the tumor core, which is basically, I'm wondering if I can, yeah, so the tumor core, which is shown in yellow and blue color, right? So we can see that in from all 3 dimensions. So if you see this part alone, right? So if you see this part, we can very well see that this particular backbone is very familiar to you. This was our method. And then we also added one additional arm here, which takes care of only tumor core. So by doing this, we were able to detect the tumor regions beautifully, right? So the top part shows the ground truth, and the bottom row shows the prediction. You can see that the prediction is very, very close to ground truth, apart from some occasional changes, some occasional mistakes, but it is very close. So we are able to get a very good method, and this method also showed better performance than the state of the art method again. So this tool was very useful in detecting various localized lesions. And now this is another example where I will also be talking about certain lightweight models. So here we talk about another kind of disease, what we call as cerebral microbleeds. So these lesions are extremely challenging. because you see the size of them, they can only be maximum 10 millimeter in size, even in the brain. So when we look at these at images, so this is what you detect, like, in the whole brain, you get these dots. And it depends on the contrast of this dot depends on what modality, but usually T2 star GRE is easy to get, and the dots are barely visible. So these are the two dots. I have shown the magnifier images here. And similarly, there are dots here for the SWI modality, and you see that they are extremely small. And if you see these two rows, the top row shows the actual microbleed lesion, whereas the bottom row shows the mimics, where these structures occur in the brain. They have the characteristics very close to microbleeds, but they are not microbleeds. So they mimic the microbleed. For instance, this is a penetrating blood vessel. These are part of sulci. So basically, the on top of these structures being small, they have a lot of false positives as well in the image. So this makes it a very challenging task, but detecting them at this stage is very beneficial because they are one of the excellent biomarkers for stroke and hemorrhage. If we find them at this stage, we can actually offer treatment course for the prospective stroke patients, thus effectively reducing the stroke rate in India, because India is right now in ranking second or third among the hemorrhagic stroke and ischemic stroke. Right. So here what do we do? So here we use knowledge distillation method, which is one of the very effective methods for lightweight model training. So here this consists of two models, the distillation framework. The first one is what we call as teacher network, and the second one is what we call as student network. So usually the teacher network is more complex, right? So here the teacher network consists of, this is the whole model. It consists of multiple parts. It has feature extractor, microbleed segmenter part, and then it has microbleed detection or classifier. So now if you look at the student model, it is quite lightweight. It has only the two parts which is present here. The third part is not available. Let's talk about the teacher model first. So the teacher model is multitasking in nature. It has two tasks, one to segment the microbleeds, and the second is to rank the microbleed patches. You divide the image into patches, and basically the model should say whether this particular patch has microbleed or not. So connecting these two very heterogeneous tasks to a common feature extractor is extremely useful, because now the feature extractor should extract the features that are um, conducive for both these tasks, that will help both these tasks. So in that process, the features become very specific in nature and also extremely relevant to microbleeds. Therefore we increase the possibility of reducing false positives. And now we come to student model. The student model does only classification, and here we give the data very specific. We give only microbleeds or the ones that are very closely resembling microbleeds, and now we want to train the model. Why do we call this as lightweight solution? Because the student model is extremely lightweight. You can see that it has only one half of the complexity as the teacher model, and basically we only for the initial training we train the teacher model once, and that's it. So when we have to adapt the model or retrain it again, so we train the student model only. So the idea is basically if we have to implement this in the clinical setting, so we will only retrain the student model and not the teacher model. So this reduces the complexity, computational complexity, and also it reduces the time required for inference. So now what is the loss function used? So the loss function is cross entropy for classification, and on top of that the distillation loss, which is scale divergence from the teacher soft labels. So you see ZS, that is a student model, and tau is basically the soft label that comes from the teacher, so which is indicated by these magenta lines here, the arrows here. So for the student model, there are two loss function. One is the cross entropy loss, which goes by this arrow, and the other is the KL divergence loss, which comes from the teacher. So now this is what we call as knowledge distillation loss. And this is useful because now the teacher is helping the student to learn the microbleed characteristics. Whereas, so this will have negligible complexity because we are not training the model, we are only inferring from the model, whereas only student trains. So we extremely reduce the computational complexity and we can use it easily. I wouldn't say edge devices, there has to be still more reduction on computational complexity for that, but we can use it on a very nominal GPU device. So now let's look at the results. So the first thing is basically the performance. So by using this to knowledge distillation, are we compromising on performance? Definitely not. So using just a simple student model without knowledge distillation is basically giving, that's shown in the green plot here. So that has very less performance compared to the black plot, which actually goes with the knowledge distillation, right? So even using the teacher alone, which is basically the blue plot, even that is not coming on par to the this lightweight model. And the second we want to know is how good are the features corresponding to microbleeds and their mimics. So we want to achieve a very good discrimination between the features. So the whole idea is to identify and distinguish microbleeds from the mimics. So what we want to do is that we want to basically distinguish the features, and we want to check how far away are the microbleed and non-microbleed features in the latent representation. So what we call as the feature space of the deep learning model. This is one type of explainability where we can show how the model is treating different features. So using knowledge distillation, we can see that the orange ones are microbleeds and the purple ones or blue ones are non-CMB candidates. So basically, we can see a very good discrimination between the microbleed and non-microbleed uh, instances. Whereas without knowledge distillation, we see that there is a very high overlap. So the model is not really able to discriminate between microbleed and non-microbleed. So if it has to put a discrimination or decision boundary, so this distillation helps it to discriminate it better than the non-distillation, the usual thing that we do. So I just want to ask any questions so far? Before I move on to data and label based limitations, so I would prefer if you ask any questions that you have so far on this.
As participants, you can unmute, you can and ask, or you can type your question in the chat window. Madam, actually, triplanar unit you have told regarding three units you are using in the axial, coronal, and sagittal. So there you are treating the image as a DICOM image format, right? Uh, there only we'll be getting it as a slices.
Hello?
Yes, madam.
Yes, sorry, I lost my internet connection here. Okay, so yes, any questions so far?
Yes, madam. Regarding triplanar unit,
Okay,
so you said you are using three units,
yeah,
coronal, axial, and
yes,
sagittal.
yes.
Okay, so you are getting the image as a DICOM images as slices, or not in the Nifty form, right, madam?
Yeah, so basically the data is given to us in Nifty form, and then we convert them into NumPy arrays because I work on Python, and
Okay.
these images will be 3D NumPy arrays of for from which I will get the 2D slices, again NumPy arrays, and then I will get the output as NumPy arrays, and then I will combine them again as the 3D input, and this 3D input I will convert it back to Nifty. So DICOM, we don't get images as DICOM, especially MR from this particular hospital. CT images we used to get, but in India, I'm observing that DICOM is more commonly used. Yeah,
Okay, madam. Thank you.
but we can also apply this on DICOM images also. You have to convert this into some form of array or somewhere how you in your comfortable space, like array space where you can apply this model.
Yes, madam. Thank you, madam.
Okay. Um, right. So I think we are currently at around 5:35. So before I start the data and label limitations, maybe we can take a 10 minutes break and start again at quarter to 6. So I can start the second part of my topic if that's okay.
Okay, madam. Okay, okay, madam.
Yeah, okay, thank you. I will see you again at another 10 minutes, which is 5:47. Thank you.
Thank you.
What can be really useful is some of the semi-supervised, as I have indicated in this figure. So the first one is for multiple modalities out of distribution sample selection. So given a very bad quality data comes into the, into your group, like when you access data, when you ask for data, not all the instances are of very high quality. So if it's part of data set, so how can we easily find out and eliminate the bad quality images using out of distribution sample detection, and manual segmentations used for the segmentation tasks. So when you have full manual segmentations, as I have shown here, so that is fully supervised. And when there is some instances where you do not have manual segmentation, so there, semi supervised or self supervised methods can be used. And there is also something called weak labels or weakly supervised methods, where the clinicians do sit and annotate, but they do not actually do a very good job because of the lack of time. So they do very basic scribbles, or they just put a circle indicating that this is the structure you want to detect, and they don't cover the whole area of the subject, sorry, whole area of the disease sign, just part of it. Or they even put a dot saying that for very small lesions they cannot zoom in and mark all the lesion boundary, so they will put a dot saying that okay, this is the lesion you want to detect. Right. So how do we handle, the lesion detection process if that is the case? So to overcome the shortage of data, so this is again one of the work of one of my students. So we work on simulating the lesion ourselves. So we don't rely on only the real lesions to train for various tasks, but rather we actually simulate or generate the lesions by ourselves, and then we use that for any task. This is extremely useful in low data regimes, where you do not have sufficient amount of training data, where you can supplement the data with your own data by simulated data. Let's look at the simulation process itself. So the first step is noise induction. So we take the healthy tissue and then we add noise to it. So one innovation we did here is to add the noise which is intrinsic to that particular modality. For instance, there is, when the image is acquired by a sensor, right, the sensor actually injects some noise into the image. The process is not entirely noise free, and what distribution the noise belongs to depends on the modality. For instance, the noise in CT images are heavily Gaussian in nature, whereas the noise in the MRI or Reggian noise, or what we call as the noise coming from Rice distribution. So here, and we use ultrasound is also, you might have heard about it. Ultrasound has speckle noise. Here we use Perlin to model the speckle. So the noise profiles are given here. So what we do is we take a patch of normal healthy tissue and we add this noise to it in a very, in a quite drastic manner, to show that this patch is having pathology that is different from the other healthy tissues. So we used four modalities here. The first one is MRI. We used brain MR, and CT. We used liver CT, and fundus imaging, like color image, RGB image. We used retinal fundus imaging, and then ultrasound. So we used breast ultrasound imaging. So the next step is we have to put the noise somewhere on the image. So we take the shape priors. We use ellipsoid, models, and we determine the boundary of lesions. The shape of the lesions are determined by the ellipsoids, and then we put the noise on top of the image, and then we use different contrast scalars as well. These contrast scalars determine whether the lesions that are simulated will be high intense or low intensity, and also like how much should be the contrast. Some examples I'll show in the next slide. So this is what we do to generate the lesions, and then we use these simulated data set, we mix it with the real data, and then we have, now we can generate as many data sets as we want. And annotation is not difficult because we, since we are simulating, we have the shape prior. In fact, we determine the shape prior for simulating the lesions. So that is quite important. And then we have using these inflated data, we train our models. So here I have shown some examples of simulated lesions. So the last column here shows the actual real lesions, and from starting from the first to the fifth column I have shown the simulated lesions. So starting from high contrast to low contrast. So first one is brain tumor. So this is the real brain tumor, how it looks like, and this is what we have been simulating. And you can see that this has high contrast compared to the last one, and this is hyper intensity, again higher to lower contrast simulated lesions. And these exudates, which are early signs of diabetic retinopathy. So here we take it on the retinal images. We generate the lesions on retinal images. We can see from high contrast to low contrast. And the liver tumors, where we generate tumors of different contrast. And finally breast ultrasound tumors. So these malignant tumors also have been, like, circled ones are the simulated ones, whereas the real one looks like this. So we also wanted to see, similar to the T-SNE plot that I was showing before for microbleed versus mimics, we wanted to see how close in characteristics the real and simulated lesions are. So for that purpose, we have plotted the two characters, the two classes. The orange dots show the real lesions, and the blue dots show the simulated lesions. So we can see from these plots that the real and simulated lesions have very similar characteristics. There is a very heavy overlap between them, and there is also good spread across lesions, right? So this shows that the heterogeneity in the lesion is very nicely captured by both the simulated lesions and the real lesions. So in all the modalities, we can see that there is good overlap between real and simulated. So we can see, and also visually we can see that the simulated lesions are quite good. Now we use it for segmentation of anomalies. Our main aim is actually to segment these anomalies. So the fully supervised, the FSUP actually tells, gives the performance or gives the output of the segmentation only using real data. Whereas in the DA and FT are two setups. DA is augmenting the data with simulated lesions and training the model from scratch. And FT is basically first pre-training the model on simulated lesions only, and then fine-tuning on real lesions. So both of this, the setup 2 and 3, DA and FT, involves simulated lesions, whereas FSUP involves only real lesions, but they are very small in number. For instance, for this data, we had only 40 real lesions in total, 40 images with lesions. That's all we had. This is very small. So for those who work on deep learning knows that this is actually a very, very small data set to work to even train the model in a satisfactory manner. But we have simulated somewhere around 200 to 250 samples, which we added to the real samples, and then we trained the DA and FT setting. So you can see that the yellow voxels are the true positive ones, the red ones are false positives, and the blue ones are false negatives, the voxels that are missed out by the prediction. So the fully supervised method actually has missed out this whole lesion, which is being satisfactorily picked up by these two settings. And also the same case here for the liver tumor, lot of missings, both the lesions are missed out completely, whereas we have actually detected it quite good with. There is also some miss with the data augmentation, but it's still better than the fully supervised one. And the same goes for hyperintensity. The challenge here is that these lesions are small. So despite that, by augmenting with our simulated lesion, we are able to get better performance. And then for breast ultrasound, so we have missed out this whole part of tumor Therefore, we will not be, if we had gone with this, our tumor volume, which the system predicted, would have been very less compared to what we would detect. So, but whereas the DA and FT gives the whole extent of tumor. The same goes for exudate in the retinal imaging setup as well. So we also did the average prediction maps by blurring the images and then using the same model. So oftentimes, what people do not usually do is that they don't quantify the uncertainty of the model. So when the model makes the prediction, we need to know how confidence, what is the confidence level of model for making that particular prediction. So that is what we wanted to predict. We wanted to determine. So we blurred this image at a different sigma using Gaussian blurring, and we applied the model across all the images, and now these are the results average. So we can see that the main uncertainties are coming along the boundaries, whereas see in the middle of the lesion it's always having high score, which means the model is extremely confident that it's lesion, which is understandable. Only along the boundary the model has some problems, and the more the problem it has, the lesser the confidence of the model is. So we have, for instance, we have the confidence is very low here, whereas for DA we have very high confidence in liver tumor. The same for breast ultrasound, the confidence is varying a lot, whereas here it's almost white. So the same here as well for retinal imaging also. So this shows that by adding some simulated lesions or by adding more data for training, the model does much better. So the confidence of the model goes up, the detection capability of the model goes up. So this is something that we discovered when we were working on this, that not only number matters, but also the heterogeneity in the data also matters to train a very robust and reliable model. So the next thing I'm going to explain is the explainability of a model for medical image segmentation. I also gave you an example, right? So let's say that you are saying whether this patient has disease or not, yes or no. We want to know what features in the data contributed to this decision making process. For instance, there are saliency maps where we can highlight regions of an image that can, like, the heat maps that can highlight different regions which are responsible for making the model's decision. And the second is GradCam, which is the gradient weighted class activation mapping, which is also very similar to gradient saliency maps, but the main advantage of GradCam is that it can actually give you these heat maps just from the classification models. Whereas what I mean by classification is that at image level, let's say that whether dementia is present or not, and then from there GradCam can give you which part of the brain is affected by dementia. And then SHAP, which is Shapley additive explanations. So this quantifies the importance of features depending on how much is their contribution to the final decision making. They use additive models to do that. And the final one is LIME, which is local interpretable model agnostic explanations. So this breaks down the data into small parts, and then it actually gives us an idea of how important each of this part is. So it gives local explainability. That's why it's called local interpretable model agnostic explanations. So all of these are visual explanation methods which gives a bit more insight into the deep learning decision making process when compared to getting a simple yes or no as an output. So I'm going to again show an example from our students' work. So where we were using the GradCam based weekly supervised segmentation of intracerebral hemorrhage. So we not only explain how the model works, but use those explanations to create labels for training our segmentation model. So given only image level presence of whether the hemorrhage is present or not, we take that information and we actually generate the segmentation labels to train the segmentation model for detecting exactly where the hemorrhage is present and the boundary of the hemorrhage. So the pipeline goes like this. So we train the classification model, and then we, from the classification model, so we actually determine the class activation map. So how do we get that? Let's say, for example, this is the classification model. So we pass the image through the layers, and finally we have the final softmax layers which predicts different classes. In our case, there is only two classes. One is hemorrhage present and another is hemorrhage absent. It has to classify between these two classes. And now what happens is that we introduce something called, so this is how CAM works. So there is a module called global average pooling, which is called as GAP. So what exactly this method does is that there is multiple layers, there is multiple channels in each of the activation map. So it creates a channel level weights by adding the activation values. Each of these activation map has feature values. It will add this and it will give the consequent values, the scalars, as the weights, and these scalars will then contribute to the final classification output. Now what happens, how do we get these CAM maps, the class activation final map, is that we take each of these values and multiply with the corresponding channel. So the first weight will be multiplied with the first channel, the second with the second, and the last with the last, right? So we actually multiply with these corresponding channels, and then we add everything together, and then we end up with this heat map. This is what we call as the class activation map or CAM map. So here I have shown the hemorrhage part, hemorrhage area indicated in the white circle, and if you see here, the CAM map highlights this area. Now it's very clear that the CAM map actually gives us an idea of which region the model takes into account to make its final decision. The model is clearly portraying to you what it is looking at in the whole image. Because there is a hemorrhage here, the model is able to say that this image is a hemorrhage image. But what we do after this is the explainability part of it. But what we do with this is that we post-process this to get a segmentation output using the k-means clustering. Within this area, we do a k-means clustering to improve the segmentation label. And then we have this segmentation binary mask, which is what we used as the annotation from experts. Here we do not have annotation, but we have created the annotations with which we will actually train the segmentation model. So some of the results here. So the first column shows two example images, and then the second column shows the saliency map obtained from CAM. You can see that the area of having lesion is highlighted, but it is not quite precise. So we did some post processing to make it more precise, and now we can see that it is more or less lying on the lesion. And finally we did the post processing using k-means clustering and then generated the segmentation labels to train the model, and this is the final model output. So we can see that the true positives are quite correlating well with the actual hemorrhage area, and we can see that the lesions are captured quite nicely by the model, showing that even without having the annotations, we were able to generate annotations. So we saw one example for low data regime where we don't have much data, where we are simulating the lesions ourselves and overcoming that problem to certain extent. And here we do not have manual annotations, but we have quite a lot of data. So there are two extremes to it. So here since we had lot of data, but only the problem is we do not have segmentation label, but we had only image level label. We are tackling it using some weakly supervised method here. So now I wanted to introduce this concept of domain adaptation and privacy protection. So I already mentioned to you that the data coming from clinical setup, the medical imaging data is highly sensitive. It has to be anonymized, but we also get data from different sources. Let's say one hospital is giving us 20 scans and another hospital is giving us 40 scans. We cannot really say no to this 20 scans because any data we get is very important. So, but there is a challenge here. The problem is that the data is coming from different hospitals. So the imaging protocol set by the radiographers are very different. So even here, if you see, most of the training data are having various contrast. They are not having a single contrast. So some of them are lighter, some of them are brighter, whereas the test data is all quite darker. Right, so we want to test it on a clinic where the radiographer is not very well experienced, so he doesn't set proper protocol, so they end up getting dark lesions, dark images itself. The contrast is also very low. So this is what we call as domain shift. There is a shift in characteristics across different domains. And what is domain adaptation? Domain adaptation is nothing but it transfers the knowledge from one domain to another domain, different domains, by leveraging the domain invariant features. There are certain domain variant features, which is the contrast here. The contrast is varying a lot across different domains. But if you want to develop a model which can adapt across different domains, the main idea would be to basically train the models which will always leverage the features that are common across domains and leave out the features that are different across domains. For instance, here the model can actually look at the features that are relevant to the brain areas, brain anatomy, which are constant across domain, because brain is like, the anatomy of brain is same for subjects. Whereas the model can actually disregard the contrast or intensity information because it's of course changing across different domains. So this is what we call as domain adaptation. It's a very active area in medical imaging. So people have, the research happening in this area has exponentially increased and it is still going high. And there are a lot of open research areas in this field. And one such area is federated learning, which is very much related to the data privacy protection. So let's say I told you earlier that there are two clinics which has given me data, like 20 subjects from one clinic, 40 subjects from another clinic. But now what if the clinics are not ready to share data? Let's say they have not got patient consent to share data. That's especially in West and now in India also, patient consent is very very important. They have to consent to share their data because medical imaging data is very sensitive. Let's say if a patient has tumor, they might not want to reveal it, they might not want to share the data. So the doctor cannot share their data without their consent, right? So let's say that this problem exists, the data cannot leave the clinic. That is one of the conditions they have. So this is where federated learning can be extremely useful, where let's say I have shown an example of 4 different hospitals here, and the lock symbol indicates that the data is not available, it's locked inside the hospital. Now what will you do? Now this is where we use federated learning, where normally we will share the data and train the model, but in the federated learning the data is present in the individual hospitals only, the data is not shared. Conversely, the model parameters are shared. So we don't share the data, but we share the model. So what happens is there is a local model. So there is a centralized server where there is a global model, and there is a local server in each of these hospitals where there are local models. Now, the model will be shared on the data that is provided. In that way, the third party will not have access to the data. The model will be trained within the institute or the hospital itself. And then these local models are available now fully trained. Now what happens is the model parameters are then aggregated and fed back to the global center. So this is what we call as federated learning. This happens sequentially, iteratively. So for example, the local model trains for 5 epochs and then the aggregation happens at the 5th epoch, and then it trains for another 5 epochs, the aggregation happens in 10th epoch. So now this happens iteratively, the model gets updated. Now because this global model is aggregated from all these local models, so they have the characteristics that is obtained from all these data, but not by seeing the data. So the data is there in their own premise, but the model is robust to all the clinics because they all participated in the model training. So this is what we call as federated learning, and this is also gaining a lot of attention. There are many open research areas in federated learning as well. For instance, what if I'm training and in the test time there is one more client added in the test time? Let's say 4 clients are participated in the training, but what if in the test time 5th client has to be added? So these are some of the challenges here, right? Aggregation, synchronization, how can we ensure that, for instance, here there are 5 subjects and here there are 5,000 subjects. This model will train very quickly, this model will not. So when do you synchronize? How can you ensure that all the models are aggregated in the same time? So yeah, it doesn't come without challenges. There are challenges and people are working on that. I just wanted to introduce this topic so that you can appreciate that there is this problem in medical imaging as well. Now, this is my last topic where I'm going to talk about opportunities and future directions. So, the first thing is interpretability and trust. It's extremely, I cannot emphasize how important it is in medical imaging to talk about interpretability and explainability, because the risk quotient in medical imaging and healthcare is high. The doctor is answerable to patient, and if any decision they make has to be explained to patients. And because AI can be used as an assistive tool for the clinicians, they have explainability component that has to be transparent to clinicians also. So for instance, the feature based saliency, this is what we saw right now. We saw an example, and there can be output class probabilities where instead of giving whether this voxel is lesion or not, it can break it down. It can say that the voxel is 25% background, 35% it can belong to ventricle lining, or 40% confidence it might actually belong to lesions. So by saying so, you do not say whether it's a lesion voxel or background voxel. You are giving some grayscale here, so the doctor can make the decision. It reduces their time because you have consolidated all this information. They don't have to look at it. But if they look at this grayscale information, they can get a better idea than what you give us binary information. The last is example based explanations. So this is extremely useful in training new radiographers, where the AI model can be used to generate examples of different cases. Pathological case should look like this. Normal healthy controls should look like this. So how can we use these examples to really train the radiographers, or even train the model? A teacher model can generate all these instances which can be used to train the student model, for instance. And the second aspect is out of distribution detection. Let's take a scenario where the model is trained to classify, let's say, 3 classes. Okay. Now, while applying the model in a specific clinic, I'm finding that there is a fourth type of pathology which the model has not been trained for. So currently what would happen is, because the model knows that it has to put the instances in one of these 3 classes, it will put the fourth class into one of these 3 classes which it's closer to. But that's not actually true. Ideally, the model should say that I have very low confidence in predicting this fourth class because I did not encounter anything like this during the training. Currently, the deep learning models lack that. So we have something called open set recognition, where the model should be able to identify what are the confidences in finding each of the classes, and also if any of the classes is not be encountered. So this is what we call as an open world problem, where we do not know all the type of lesions that we are set out to determine. So that is also one of the very open problem, and it's one of the future directions in the research, where this open set recognition, when we combine it with the federated learning, like different lesions in different hospitals, it's a huge problem, and it's a very valid and very interesting problem as well. And the last one is accurate extraction of underexplored biomarkers. So in medical imaging, as is the case of any research domain, it's highly exploratory in nature. So we have been working on different biomarkers like microbleeds and hyperintensity, which are related to dementia, neurodegeneration. But we are not there yet. So there are a lot of unexplored biomarkers or signs that appear in the brain as a result or as a precursor of dementia. We are still researching about it, and extracting these rare or underexplored biomarkers would also be important. Maybe they have not been studied so far. This falls under the scientific needs that I was talking about in the initial slide, right? Where we want to understand more about the disease and get an idea about their role in the final quantification of the disease. So this is what we want to do, and also characterization and reporting, where the natural language processing NLP comes into fore, where we actually use the language for reporting what the model gives as a binary output. We can actually report it in a more understandable format, because clinicians write reports, right? So that's more understandable to them. So these are some of the very cool opportunities and future directions that are currently existing, and a lot more. I'm just highlighting some of the ones that are relevant to what I have shown you so far. So I hope this was informative. With this, I conclude my lecture. And thank you very much for your attention. I would like to thank my research groups and collaborators and the funding bodies which have been able to do my research. And thanks again for your attention. I would take any questions if you have.
Thank you, madam, for your insightful session.
Yeah.
Participants, if you have any question, please. Madam, there is one question from
Oh,
Chandra.
yeah, there were actually a couple of questions from the chat. Let me just have a look at it. Okay. Let's come from the beginning. So how are you ensuring that all software libraries used are working as intended without malfunction? So we do use pre-existing libraries. Most of the times we use Python and deep learning libraries like PyTorch or TensorFlow, so which are mostly established. So sometimes we might have to, you know, process our data in such a way it's compatible to the libraries. But that is pretty much it. So we don't usually encounter any malfunction because these uh, modules are computational, not experimental. So I hope that clarifies the question. And the next one is, oh, okay. So you are talking about validation. Yeah, that's actually a very good question. So, how do we validate? So, what we do is that we have multiple data sets that are available for validation, which we do not use for the model development process. And we also do extensive clinical trials and testing before the data or the tool can be actually integrated into the software platform, because failing to do so will not provide good results on multiple domains. So that is something that we take seriously, and also do extensive analysis and validation before integrating it into a clinical tool. And also the tools like FSL, where my tool has been aggregated in Oxford domain. So there is also a live feedback facility available where the users can actually, there is a forum available where they can register their complaints if there is something. So we repeatedly, update our tools in case of any. So far there has been not been any serious concerns regarding our tools, which means that the validation phase, we take it really seriously, and we do several preventive measures to avoid any malfunctioning, or what you call as a severe lack of robustness in the models. So how are you, okay, the same question again. Are you using any cloud platform or local environment? Ideally, cloud platform can be used. The main problem is the computational complexity. So we sometimes, all of these cloud platforms are on payment basis, as you all know. So the higher the computational complexity, the more the price that we have to pay. And also they might not be adaptable to real life settings as well. So in our lab, in our group, we actually work on local environment. We have servers, but we do run some training programs in the cloud platform as well. For instance, I think this is a good time to say that as well. So I organize routinely medical imaging workshops in association with Siemens. So there we actually do practical sessions as well, and for those things we usually use cloud platforms. Because the computation involved is not very intense. So if you are planning to use cloud platform, please be advised of the fact that you have to choose appropriate platform which has the required GPU servers and also the storage facility to store all your data, because imaging data can take a lot of storage space compared to the textual data, or even one dimensional data or tables or those kind of information. Okay, those are some of the questions I see. Apart from that, if you have any questions, I'd be very happy to answer. Okay. Apart from GradCam method, do you have any XAIT? A lot of them actually. So we have, as I showed you, there was a slide on that. So where is it? So it's here. Yeah. So we have saliency maps. These are also not exhaustive. We have more methods. GradCam is the most common method, so I thought you guys can relate it to the topic very well. But we do have saliency map, we have label representations, we have layer-based representations. So if you go and search explainability for medical imaging, so you will get a lot of visual tools or visual attributes, quantitative metrics also available. What is lacking right now is the proper benchmark. Let's say that even in our case, right? So let's say that this is the a place where CAM is present, and how can we evaluate it? We cannot really evaluate it, right? So right now we are evaluating with the downstream task. So we use it for segmentation, and this segmentation output we can evaluate, right? But we cannot evaluate how good the CAM is. So such benchmarks would be really nice. People are working on it, but there are various visual methods that are available. Yeah. So that's these are the questions I see. I don't
Yes,
see any more questions
yes,
actually.
madam. Thank you, madam, for your insightful session, starting from basic deep learning architecture, novel architecture, till up to domain adaptation and federated learning. Thank you for your wonderful
Yeah.
session. Thank you for your time. Thank you.
Great. Thanks for the opportunity. So I am also aware that there is a test or something available. Should I be present for that? Not
No,
required, right?
madam. No, madam. No, madam.
Okay, great. Thank you very much. I wish you all good luck with your program. Thank you.
Thank you. Participants, please stay back for a valedictory session. I request all the members to be here for maybe for 10 to 15 minutes.